And the last podcast is on the famous ideal gas law. First we talked about Boyle's law, which shows the relationship between pressure and volume. Then we talked about Charles's law, which talked about the relationship between temperature and volume, and then Lusak's law, which talked about temperature and pressure. And when you combine all three variables, pressure, volume, and temperature, you come up with the combined gas law. Um, and then now we're going to introduce the mole into the equation. And it's actually a much simple formula. It's actually, I personally think it's easier than all four of these formulas. This one's actually the easiest, and it's probably the one you're going to encounter the most because with this formula, you have all three variables: pressure, volume, and temperature. But the only difference is that it incorporates the moles. So, what is the pressure if you have 1 mole of this gas? Or what is the volume if you have 30 moles of a gas? And then you have an R, which is a constant. And a constant is a number. You just have to find it on the formula sheet and determine the units so that the units end up canceling at the end. It's not a bad equation. It's also known as a pervert equation because it's per PV equals nRT, kind of resonates with the word pervert. I don't know if that's appropriate, but that's what some people call it, the pervert equation. I call it PV equals nRT. So this is called the ideal gas law. It's the most famous of the three, of the four, or I'm sorry, of the five, and it relates all of these variables. So PV equals nRT. You're probably going to want to memorize this formula. All the other ones you don't have to memorize, but this one's probably one that you should memorize. R is a constant, and the value of R depends on the units. So you might see 4 different R's, you just have to choose the correct one. So if we look at these 2 R's that I gave you, one says 8.314, the other one says 0.0821. They both have liters in it, but this one has atmosphere for pressure, and this one has kilopascals as a pressure, moles and Kelvin. So if the problem gives you kilopascals as a unit of pressure, then you're probably going to want to use this R. And if the problem gives you atmospheres, then you're going to probably want to use this R. And don't worry, we're going to have practice with this. There are 4 examples, I believe, in this one. So for this example, it says how many moles of gas are contained in 22.4 liters at 101.325 kilopascal and 0 degrees Celsius. So you look at the question and we're like, okay, it has moles, so we're obviously going to be using this equation because this is the only one that has N in it. So what we're going to do is we're going to write our formula down. That's the first thing we always do, right? I don't know where to start, but I'm going to write my formula. So my formula is PV equals nRT. Let me rewrite that. That's awful. So the equation is PV equals nRT. Okay? And the question says how many moles. So we're looking for N. We're looking for this guy. So we're going to divide whatever's next to it to the other side. And that's our new formula. Our new formula is N equals PV over RT. Okay, that's our new formula. Now we're going to start plugging in numbers, but you're probably asking which R am I going to use? Well, let's look at the pressure units. They gave us the pressure in kilopascals. So are we going to choose the R that has kilopascals, or are we going to use the one that has atmospheres in it? We're going to use this one, okay, the one that has kilopascals in it, because we want the units to cancel. So let's do that. Pressure is in kilopascals, so we're going to write 101.325 kilopascals times the volume, which is 22.4 liters, divided by the R, which we determined we're going to use the first one because it has kilopascals in it. So 8.314 liters times kilopascals divided by mole Kelvin. Okay, so then we put the temperature, which is in Kelvin, 273. Okay, and if you look at the units for the constant, the kilopascals cancel, the liters cancel. So make sure it's in liters because if the constant has liters in it, that means our volume must be in liters. Moles, which is what we want, so that's not going to cancel, and the Kelvin does cancel. So what we're left with is moles. When you multiply this and divide by this and then divide by that, you get 0.9999 moles. Okay, so that's your equation. In chemistry, I'm not going to explain it in detail, but what I just did here in this problem is I just proved something in chemistry. In chemistry, if you have 1 mole of a gas at STP, meaning that it's at 0 degrees Celsius and 1 atmosphere, the volume of a gas, it doesn't matter which gas, is going to be 22.4 liters. And I just proved that in this example because it says how many moles of gas are contained if I have 22.4 liters, and this is the same as 1 atmosphere. So if you look at your notes, 1 atmosphere is equal to 760 millimeters of mercury, or it's equal to 101.325 kilopascals. And 0 Celsius, which is STP, then if we have 22.4 liters, it should equal to 1 mole, and that's exactly what I got, 1 mole. So I ended up proving this algebraically. You don't have to know this, but I just thought it was pretty interesting. Because I just proved something, one of the laws of chemistry. So here are a few notes that will guide you a little bit. And don't forget about this slide where it says remember, use the correct R, make sure your temperature is in Kelvin, make sure your answer includes units. I'm going to be very picky with units this chapter because it needs to be in the correct units. Okay, before I was a little bit lenient. Now I'm going to not be happy if you don't put the correct units. For example, 2, for this one, it says how many moles of air are contained in 2 liters, this many kilopascals, and this much temperature. Go ahead and see if you could do this using example 1. So go ahead and pause, try, and then go back, okay? Okay, so now that you tried to do this problem, because the only way you learn chemistry is by trying and figuring out your mistakes. So the question has moles in it, so we know we're going to be using PV equals nRT. And it says how many moles, so we're going to solve for n. And when we solve for n, we get a different equation. PV equals nRT turns into this equation. And now we start to plug things in. This is where we need to be careful. P is 98.8 kilopascals. The volume is 2 liters. Our R value is 8.314. liters times kilopascals divided by Kelvin mole, something like that. And then the T is 25 plus 273, which is 298. Okay, so 298. And you have to double check the units. So kilopascals, it cancels. If this was in milliliters, you would have to turn it into liters, but it's already in liters. If this was in Celsius, you turn it into Kelvin, so the K's cancel, and then you're left with moles. And then your answer should be 0.0798 moles. So if you have a 2-liter flask and it's at that pressure and that temperature, that's how many moles of gas you would have. Okay, so now let's try example 3. So for this one, you go ahead and try it. It says pressure. It doesn't specify if the unit. So your answer, you could have 2 different answers depending on what units you choose. So I'm gonna do it both ways. But you could use the first R to get it into kilopascals, or you could use a second R to get into atmospheres. It doesn't matter, and I'll show you why. Okay, so go ahead and try, and then now that you tried, let's go ahead and work through this one. So for this one, it says calculate the pressure, and we write our PV equals nRT equation, and we want the pressure, so we get rid of the volume that's next to it by using math. So now we're gonna plug in for N, and it's 43 moles. The R depends. Which one do you want to use? So let's say we use this one, 8.314 liters times kilopascals mole Kelvin. And T, it has to be in Kelvin, so 278 Kelvin, because you just add 273 here. And then the volume is 65 liters. It matches with the constant units here. So liters and liters cancel, moles and moles cancel. Like if this was in grams, then you would convert into moles using the molar mass. The K's cancel here, and you're left with kilopascals. And when you do the math, you get 1,529 kilopascals. The other way you could have done it is you could have used the other R. So when you solve for P, you get this again, and the moles stays the same. But let's say you use the other R. Let's say you use this R, which is liters times atmosphere mole Kelvin. So the only difference again is the unit of pressure, and when you do the math, you get 15 atmospheres. It doesn't matter, both of these are correct, it's just that they're in different units. So for example, in the beginning, let's say the question says find the answer in kilopascals, but you're only given this R, let's say, then at the end you could just convert this, just do a simple conversion. 15 atmospheres times 1 atmosphere has 101.3 kilopascals, because that's the conversion factor according to your notes, and you still get a number that's relatively close to this number right here. It's not the same, exactly the same, because I rounded, but we could say that it's the same. So that's 2 ways you could do it. Okay. So now go ahead and try example 4, and see if you could get this answer. See if you could get 1,968 liters. Okay,